Tim, does it work? Yes. Tim, thanks for the great introduction. Yeah, I rarely get introduced in this way. So, first of all, I would like to thank Marco and all the organizers for inviting me here. It's really a pleasure coming here. Thank you all for coming here. I think this is really an extremely important topic for the future of chemistry. In my talk, I would like to elaborate a little bit on the basis, actually, of what we needed to apply AI, and specifically from a catalysis point of view. And I would also like to start with a little bit with the bigger picture. What are the challenges in chemistry, and where I believe AI can help in the future? So, during my talk, I will start setting the stage with some example of grand challenges. Then I would like to introduce you the German digitalization initiative. I have a short video on that, so there will be a break of 4 minutes in between where you can relax. And then I would like to give you, at the end, some case studies. So I think most of you are very familiar with this concept of the so-called Earth Overshoot Day. This basically is a statistical method and gives you a certain date when basically all the renewable resources or the biocapacity which is available on Earth has been used, and if all the people on the world would live, probably I should put this a little bit more to the mouth, so if all the people in the world would live, for example, like people in Austria, the biocapacity would be used already on 6th of April of this year. And you can see also very often we believe here in Northern Europe, we are, let's say, on the front runners. We are very sustainable. In fact, we are not. Germany, the date for the Netherlands, for example, it's April 12. Germany, it's May 4th. So it's basically, it means we would need, if everyone on the world would live like we live here, we would need more than 2 worlds, 2.5 or 2.7 worlds. The reason why we run out of this equilibrium is, on the one hand, of course, we have an increasing mankind. The biocapacity basically decreased over the last 50 years. Until the 1970s, it was still in equilibrium, and since that time we're running out. And it's absolutely clear that there is no second Earth, there is only one Earth. So the main challenge for all basically industries, or the basis for everything, is we have to come back to an equilibrium, because our resources are run out. We cannot live with 2 Earths. And of course there is not only one technology which can achieve this, but there is several, and I believe AI also can contribute that. I will go more into detail at the end. The second thing, what we see is also related to that, that's the climate change. Climate change, you might say, okay, what's the problem if we have today not 12 but 13 degrees? It's, in fact, it's a little bit more comfortable. In fact, the big problem, again, on a global scale is, of course, it's not the rise of the temperature, it's the effects associated with climate change. And if you look, for example, by metadata on studies on biocapacity, production of food, for example, then you realize that specifically in the southern hemisphere, the biocapacity will be decreased for the main, let's say, important food by up to 50, by 30 to 50%, and of course this will even increase the moving of people from one place to another, and as we all know, there is huge political and societal problems associated with that. So we have to also stop this. We have to stop basically specifically carbon dioxide emission or greenhouse gas emissions. And it's absolutely clear here from this picture. We have, of course, certain fluctuation. I want to, let me see, is this, yes. There is fluctuations. Please have a look here at the time scale. This is, of course, not the same. This is 1 million years. This is the last 2,000 years. There were always fluctuations, but since pre-industrial, after the Industrial Revolution, the increase actually of climate relevant gases increased dramatically. And then now you might think, okay, we're doing so many things. We read every day about it, and we have seen there should have been already an impact on that. But if you really look, what has happened in the last 30 years, not much. If you look on a global scale, there is no significant change in there. I can assure you, in the next 10 years and 20 years, the change will be dramatic, because it has to be changed. If everything goes well, what we all hope, predictions says that we will need 1.5 up to 2 times more energy until 2050. And if we use our resources the same way we are using them today, it's clear that this increase, it's impossible basically to imagine the consequences out of it. So we have to change. And how will this change look like? Of course, we have to stop carbon dioxide emission. We have to stop basically using fossil-based resources. It's a huge point. We have heard about the plastic age. The plastic age started with the first polymer made by bakelite. Some of you might know it. The first polymer still used in some applications. Nowadays, it's mainly polyolefins which are used. And you might also have heard about it in the oceans. We have now islands of plastic which have the size of France. It's impossible if you think also again about it. So of course, specifically here in Europe, we do a lot of recycling, significant amount, but definitely not enough. And thank you. And we have to change this. So, but one of the ideas, of course, to change this is to go to carbon dioxide-based materials, improving photosynthesis, for example. There is many, I would say, interesting ideas around carbon dioxide to ethanol directly, carbon dioxide to butadiene, generation of waste-based C4 streams instead of classical refining, polyester waste to plasticizers. You might have heard the term waste is the new hot stuff, waste is the new value, PVC to use for products, and many, many other ideas. Again, there will be not one technology and not one solution, simple solution for all this. It requires a combined effort. This is, I think, the main message we also have to transform to the society, because it's always easy to say, we only have to change that, then everything will be fine. It's not so simple. So, yes. How does a possible solution might look like? The possible solution for all this is a picture we created 15 years ago, and of course it's a very simplified one, but everything basically goes back to using renewable energy, available resources, specifically seawater. With the help of catalysts, you can generate reductants, because oxidants we have for free in our atmosphere. Oxygen, often we forget that's a very reactive chemical, which you can use in many chemical reactions quite, let's say, productively. So you have to make reductants cheaply, because then you can make value out of many things, for example, carbon dioxide. So if you improve this process, basically you have hydrogen, you have oxygen, you have bio-based waste, ideally non-editable bio-waste, so that you have not this problem between food and tank. And then you have CO2, because we should have and still will have industry, of course, where you can use carbon dioxide, for example, from the atmosphere. And more or less, and this is not a dream, technologies are already there for a number of products. You can make them. Of course, you have to make them competitive. And we have to think about competitive prices also. But this is not only a scientific and technological problem, it's also a political problem. Catalysis is involved in all these transformation steps. Therefore, catalysis is a specific technology of interest, actually, for chemical transformations. You might know 90% of all chemical products are made in the materials industry and the chemical industry, pharmaceutical industry, all included by catalytic processes. Catalysts accelerate and control selectively, typically, and thereby also it's a relatively powerful tool to, for example, minimize energy consumption in these industries. And it's sorry, no, that was the wrong one. It's absolutely clear also for me that there will be no carbon neutral mobility and chemicals production without catalysis. What is interesting at this point, I should mention that here also, so catalysis is very much, I think, established in biotechnology, chemical engineering, classical chemistry, material science, but less, as we have heard also in the talk of Max before, less, I think it's, although we have heard the relation here, but less it's used in mathematics, data science, and information technology. And I intentionally draw this circle like that. I think there is significant potential for more overlap in these areas. So, if you think how catalysts typically react, how they behave in certain chemical transformations, and how catalysis actually is defined, so it's a relatively complex phenomena. You have the homogeneous catalysis, heterogeneous catalysis, biocatalysis, but the general principle for them are all the same. The active sites are the central elements of all catalytic systems, and they are active sites are non-equilibrium structures, and they change in nature with high dynamics. Very often we make model catalysts which are not active at all, but because they are stable, because catalysis is a very dynamic phenomenon. And I would like to tell you now a little bit about the vision of a digital catalysis science and digitalization, which we started around 2 years ago in Germany. We proposed a network of several universities, companies, and created this group, the German word would be Nationale Forschungsdateninfrastruktur, National Research Data Infrastructure for Catalysis. And this is an initiative of a larger initiative of the German Science Fund, who created in the past 3 years up to 30 consortia on data infrastructure for all areas of sciences. And they put in up to 70 million euro funding into these 30 consortium. And 2.3 million for each of consortium is paid for 5 years, and it's expected, or these consortium can work for 10 years if they are successfully evaluated after 5 years. Here you see some examples. It really involves spread all areas of sciences. And one of these consortium is the Initiative for Catalysis. And I think this has also, I think, it provides, I think, basis also for use of artificial intelligence in catalyst science specifically. There is reports about that, sorry, that was again the wrong one. There is reports about that. We summarized the goals of this. We have a lecture series started on that. And there is, since I think 2 weeks, there is a YouTube channel where you can find educational videos on metadata, ontologies, things like that. And now it's basically time for a short break for the introduction of this. This lasts for 4 minutes. So I hope you, first of all, I hope it works. And second, I hope you can enjoy it. It's a little bit more general. Can you hear it? Okay.
and the associated metadata, and only a very limited, suitable for catalysis, infrastructure for the exchange. As a result, a lot of data generated by the effort of scientists cannot, or at least cannot simply, be used by other scientists, a situation which obviously restricts the knowledge gain from scientific experiments across the board. To note is also that not everything has to be shared, but still everything should be treated as if everybody should be able to understand the data. In order to obtain the highest possible added value from catalysis research for humanity at large, fundamental changes in catalysis research and science are needed. Based on this need, NFDI4CAT was founded as part of the National Research Data Infrastructure Initiative, or NFDI for short. The amount of catalysis research data is increasing every day and has been doing so for years, and now we aim to make such data available and reusable. Standards for catalysis research data should make the data reusable and understandable, also for other researchers, specifically according to the Research Data Management FAIR principles: findable, accessible, interoperable, reusable. Our vision is to establish an infrastructure for dealing with data in a fair and open way, and set standards in the field of research data management, as well as strengthen Germany as a science and knowledge hub, and, last but not least, transform catalysis and catalysis-related science into digital catalysis. So, what exactly is NFDI4CAT, and how does it help with all this? In essence, NFDI4CAT, or the National Research Data Infrastructure for Catalysis and Catalysis-Related Science, aims to secure the digital future of catalysis and bring together the various fields of catalysis for information sharing, and thus provide community-driven, user-centric benefits to anyone interacting with catalysis. Our goal is to shape the digital future of catalysis by enabling a transformation of industries and related sciences related to digital catalysis, and creating an infrastructure for open and fair processing of catalysis data. Part of our future vision is also to improve the ability to predict reactions, material properties, or catalysts for reactions using artificial intelligence. And for this, large amounts of standardized data are also needed, which NFDI4CAT will make possible. Thanks to a team of experienced and professional partners from academia as well as industry, this will become possible and is already on the way. Every member is a professional expert from a different context or field, all related to catalysis or data science, and together they combine their expertise and knowledge. The results are increasingly useful. We provide services and tools correlated to catalysis, education and training related to the management of data applied research and data science on data catalysis, as well as sustainable and fair infrastructure for catalysis data. Find more useful information on how we can help you or your organization, or support us, ask us questions, or simply subscribe to our newsletters to stay in touch. Join us in shaping the data-driven evolution of catalysis. NFDI4CAT.org.
Okay, so I don't have to tell you let's say the detailed partners. If you're interested in that, you can talk to me in the break also or afterwards. It was already mentioned also that this is an initiative specifically between industry and academia, which is in fact the only consortium on data for infrastructure in Germany which combines both sides. All the others are pure academic initiatives at the moment. And the main goal, as I said, is this transformation of data transfer from classical catalysis science, which you basically see here. This is normally what we do if you do molecular modeling, data exchange, DFT calculation or so. We have certain data, and then we basically, if the reaction or the transformation is successful and the catalyst is developed, we basically try to develop a process out of that. So we have multi-scale modeling, and then in the end we have process simulation. And it's not so easy actually to transfer the data for all these individual stages. And the goal of this initiative is basically go towards what we call a digital catalysis scheme, where we use the catalysis data directly for heat transfer, for multi-scale modeling and process design. And so all the experts from the various areas, engineers, let's say scientists in homogeneous catalysis, biocatalysis, heterogeneous catalysis, but also from process development are involved in this work. And shared vocabularies, persistent identifiers, quality assurance, IP question also, and all these things are addressed in this initiative. So this is an example from our own institute where we are working since 20 years basically on fair data management for heterogeneous gas phase type catalysis reactions. Also with other partners, we're doing there, for example, we develop models, for example, on reactions like dry reforming, carbon dioxide, methane, biomethane, for example, reactions. If you're more interested in that, you might look at the publications of David Linke, who is department head in our institute and has published several works in this area. At the end, I would like to tell you a little bit about good and bad data, because this is in fact I would say the prerequisite using also artificial intelligence or machine learning methods for that. And there is no difference, to be very clear, between homogeneous and heterogeneous catalysis or biocatalysis data here. There is a difference, I would say, between good and bad data. So for those, I'm not sure how many of you are, let's say, molecular-minded chemists. That means comes from synthesis, organic synthesis, organometallic chemistry, and those who are coming more from material science, heterogeneous catalysis, heterogeneous materials. Very often this is seen as two completely different areas, but in fact there is not so much difference. You can very easily actually compare a surface with a ligand structure, and the active center on the surface is not so much different from the active center of a homogeneous catalyst or a biocatalyst. As I said, dynamics play a much more role there. What we typically face as a problem in the development of a catalytic system, and I've chosen here an example from a known reaction, making adipates, which is an industrial process also involving production of nitrogen oxide, greenhouse gases. For example, it's very often you have a complicated reaction network, and developing basically the right catalyst for this reaction is you do what we have seen also in Max Rock's classical trial and error. So you look at the individual steps, improve a certain system, then you have gut feeling, improve the second step, and then what you typically do is what you have seen here. Oops, sorry again, that was the wrong one. You synthesize certain ligands or surfaces, and by literature know-how, by your own, let's say, feelings, by ideas, curiosity-driven things, you get certain data, and because of the data, then you optimize the system and you develop a catalyst. This is the classical way. This is a tedious way, it takes time, and you miss many, I would say, good results. And it's not very likely that you hit in fast time the optimal system. Here you see a different approach. 3 groups involving Tobias Gensch, also Matthew Sigman in the US. They published this phosphorus ligand library, Kraken. It's a virtual phosphorus ligand library which you can use openly on the net, for example, if you would like to use ligands for certain transformations. What they do is they generate from the ligand properties, or they create the ligand properties into 2 dimensions. It's in fact not really physical, let's say, dimensions. It's not the cone angle, for example, or the basicity. It's a combination of several things, and they create this virtual library, and then you take out selected members of this. You do the reaction, and then the system, the neural network, basically suggests you new ligands based on the results. You synthesize them, or you buy them, ideally, if you can, and then you do the next round, and then again and again, and after 4 or 5 rounds, you ideally basically have an optimized catalyst system. And we tried this together with the group of Anat Milo, who is doing machine learning algorithm for several chemical transformations, and we have chosen a very challenging reaction. One of the most challenging reactions one could imagine, for example, is the selective CH activation on a relatively, let's say, non-functionalized or similar CH bonds. And the model which we are using is shown here. So you have a heterocycle, for example, and then you have an alkyl chain. You have alpha CH, beta CH bonds, and gamma CH bonds. And the idea was to activate all these CH bonds in a selective manner, or to develop catalysts for the activation of all of these CH bonds in a selective manner. And this is not easy. Of course, you can find catalysts which can activate everything under drastic conditions, but selectively, for example, in the beta position or gamma, it's quite difficult. And we used, based on, let's say, some previous literature knowledge, we used a ruthenium-based catalyst system. We synthesized and screened over 100 ligands from that. We started with commercial ones, but then synthesized over 100 ligands. And in the end, after 3 cycles, we basically achieved good selectivities for any of these reactions. So this is, from my personal experience, a powerful example how really machine learning algorithm can improve. We would never have developed that catalyst systems, I would say, without the help of the machine learning algorithm. My last example, 1 more minute I need. My last example is also more to the audience. This is something towards the future. I'm coming back now to the point of circularity. What is important? In order to become more circular, we should not only think about selectivities like we traditionally think in, or not the traditional way of selectivity in organic reactions. We think about stereoselectivity, regioselectivity, chemoselectivity, and all of these issues. But we rarely think about energy efficiency, for example. We don't think about carbon footprint, feedstocks, and available feedstocks, and specifically, if we want to make an impact on a larger scale, we have to think more about such efficiency. So if you run, for example, synthesis of methanol, it makes sense to think about the energy efficiency. It doesn't make sense actually to do photosynthesis. Just to give you an example, photosynthesis has a total efficiency, energy efficiency of realistic less than 1%, and then use these plants to make methanol. That's absolutely nonsense. Or even one can ask about making it ethanol. The energy efficiency for making that carbon-carbon bond is extremely low. If you're using carbon dioxide, use photovoltaics and electrocatalysis, you can make the corresponding carbon-carbon bond in much more energy efficient ways. And this is something we should think more about, and I think specifically also the catalysts which we need for such transformations, machine learning approaches can help us a lot. This was actually what I wanted to tell you. I think for the future, we need effort. We need a clear mission. We need services, which we don't have at the moment in our universities. And we need also a vision where we really want to be. This is my ideas to that point. I thank you for your attention. I'm happy to answer any question if there's still time.
We'll take 1 question. One quick one. Here we go. The man in the green hat. Who looks like Thor, actually. There we go. Maybe I am.
No. Hi, thanks for your presentation. My question pertains on your first half of your presentation, where you put forward the dangers that we're living in the age of plastics, as Max put so eloquently. And I think that Max's previous presentation about information theory and how that relates to machine learning is actually a more general message where we can look at the world and we see that we have several actors, countries, industries, organizations, etc., that have a dynamics, a game theoretic, information theoretic dynamics between them. And when you look at the current state of the world and how the economy is based on oil and all this, do you think essentially that development is going fast enough in science, in politics, in the industry, or do you think that we have to face catastrophe to change the foundation, to change the foundations of the world? I mean, necessity is the mother of all inventions, they say.
That was more a comment than a question, probably. No, honestly, I think we are not fast enough. On the other hand, I'm optimistic. And I think everyone else can contribute to this. Actually, you here can also contribute. We should not only put fingers on other people and say, okay, the politicians have to change that, or that country has to change that. We all basically, this is easy, but we have to, let's say, contribute our own part to that. In my opinion, and this is probably we can discuss in the break more, but in my opinion, for example, the energy prices in general are not fair, and this is not clear to the society. For example, if you look at the price of nuclear energy, it doesn't include the cost of the waste. If it would really include the cost of the waste, nuclear energy would be in no way competitive. Carbon dioxide based in energy generation, if you would calculate the cost for the carbon dioxide, for the problems and all this, again, renewable energy would be much more reliable. But this is a global effort. And for politicians, the main point is not to change the situation in their own country, but to come to a global agreement. This is the opinion. And we as a population, or as mankind, can only contribute. Each one can contribute to that.
Thank you so much. Ladies and gentlemen.